Okay, we're going to dive into the deep end here and finish off our analysis of variance, also known as ANOVA, of course. Analysis of variance, okay? This is a complex process, and thank God that we can do this typically on a computer, and we will Zoom as a class, and I'll show you how to do this on the computer as well. But hopefully my explanation of where these numbers come from makes a certain amount of sense. Once the computations are done, a computer will do the computations. It's still sort of crucial that you know what these values are. So this is the total variability for the group. That's all 20 numbers from our data set. And we got a sum of squares with associated degrees of freedom. And like I mentioned in the last video, these two sources, the source of the variability, these two make up the total, and they are orthogonal, so this plus this equals this, okay? We have our F ratio, and we calculate that is the mean square between over the mean square within. So it's telling us the variability that we see between the groups, and we compare that to what we see within the groups, okay? So we have a value of 7.42, and I'd mentioned that, hopefully you have your book with you, I'd mentioned that we need to find the critical value for our F ratio in this case, and the critical value is found in the analysis of variance table in the back of your book. Let me see, actually, for the textbook that we're using, let me just see what it's table B4. It's table B4. And what we're going to do here, that's in the appendix. What we're going to do is we actually, whereas before when we did a t-test, we had just one value for degrees of freedom. For an F test, and again, this is a higher level of complexity here, we actually have 2 degrees of freedom, okay? And that is, we have the degrees of freedom associated with the between groups and the degrees of freedom associated with the within groups, okay? And if you look at the table, take a moment to look at the the top row and the side column, and it will tell you. They want to know the degrees of freedom associated with the numerator. And so the numerator is here, right? So it's 3 degrees of freedom, and then they want to know the degrees of freedom associated with the denominator, and that's the within group, so that's 16. So it's 3 and 16. And actually, when I'm reading this kind of stuff in a journal article, because I know that this is the number of groups minus 1, and just from this alone, I know that they had 4 groups in the experiment. Okay? So, if we look that up in the table, they give you a critical F value. The normal typeface is the F value for 0.05, alpha level 0.05, and then the bold is for an alpha level of 0.01. Let's just stick with our 0.05, and we'll see from the table that the critical value is 3.24. So take a minute, look at Appendix B4, see if you can identify, if you can find this number, right? Along the top, it says degrees of freedom associated with the numerator. That would be 3 for us. And then along the side, it says degrees of freedom associated with the denominator, and that's 16. So you kind of look across the top, find what column you need, and then look all the way down to degrees of freedom of 16. This is our critical value. Remember from the previous video that as soon as we have an F value that's higher than 1, we start to suspect that there's a treatment effect. okay? You can watch that video again. The concept is if there's no treatment, the top and the bottom will be equal, so that would be 1. As soon as the top gets bigger than, the numerator gets bigger than the denominator, then we have some indication of a treatment. But just like when we did z-scores, just like when we did t-tests, we have to compare. This is what would be our observed f value, and we can even do this, 3 and 16. Okay? We compare the observed to the critical. If the observed value is larger than the critical, then we reject the null. Okay? So, it's the same kind of logic here as our t-tests and our z-scores, but hopefully what you're noticing in this class is we keep building on the complexity, because this now allows us to do research with any number of groups instead of just 2. A t-test allowed us to do research with 2 groups. Analysis of variance will analyze the data from more than 2 groups. So, our observed value bigger than our critical value, we reject the null. Now, I didn't say what the null was when we first started this whole analysis of variance, but here we have it. The null would say that group 1, the mean, is equal to group 2, is equal to group 3, is equal to group 4. Okay? That is, there's no difference between the means. I'm going to erase this. We're all good with this. Okay? I can erase this now too. Okay? The alternative is not, we don't have only one alternative. And herein lies yet another problem, another level of complexity, because we could have a situation where we just negate all of this, where we say that they're all unequal like this, right? But that, if we use these 2 hypotheses, we actually have not exhausted all possibilities, because another possibility for the alternative would be that groups 1 and 2 are equal, but they are different than groups 3 and 4, which are equal. So this is different than this. We could have a situation where group 1 is unequal to the others, but they are all equal with themselves. Okay? To themselves, I guess I should say. And there are a bunch of other alternatives. So we don't have a simple null hypothesis and then one alternative. We have a null, but we have a bunch of alternative hypotheses. So we're gonna sort of get a little cheesy here, and we're gonna say this. Not all of the mu's are equal. Now, notice that this statement is not the same as this, right? This includes a whole bunch of different configurations of what the differences might look like. Not all of them are equal, but it doesn't say they're all unequal. Okay, so we're not going to use this. We're going to say not all of the mu's are equal. We do reject this, right? Our critical F value was 3.24. Our observed F value was 7.42. Okay. So we're going to reject the null, but we don't know which groups are not equal with other groups. Now, I'm talking about mu's here, and we're going to use our sample means as guesses for our mu's. If I look up at my data set, I suspect I know what's going on here. It looks like the Taylor Swift music group is not remembering as many words as the quiet group, and it looks like the quiet and the white noise are about the same, and it looks like the white noise and the Taylor Swift without lyrics are the same. But of course, statistics and science are not really up to just eyeballing this and making a guess about what's going on. So believe it or not, we need to do one more step before we're finished here. Okay? We need to do one more step so we can decide which of these alternative hypotheses is likely to be the case. We reject this. They are not all equal. Okay? But we're trying to decide which of the groups is equal to or not equal to another group. Okay? And so we're going to do what's called a Posthoc test. And that means after the fact, right? So after we do our analysis of variance, we're going to use a Posthoc test. In our case, we're going to use something called a Tukey's test. And it's called the Tukey's HSD. That stands for honestly, and I'm being honest about this, honestly significant difference. Honestly significant difference. Tukey's HSD. It's pretty simple in terms of its computation. At least I should say pretty straightforward. But let's do this, and it is the value of Q. Now, I'm assuming you're saying, oh my God, what the hell is Q? Well, we'll get there, okay? Times the square root of, and let me just make sure I'm doing this correctly, right? The square root of, I'm getting this from the textbook, page 428. The mean squares within, mean squares within, do I have that? Yeah, I can just look at my chart over n. This is the sample size for each of the treatments, okay? Now we happen to have equal treatment size. If it was unequal, you could get the average perhaps, or there are other alternatives. By the way, Tukey's test is one of a variety of Posthoc tests. So there's Chaffee's test, there's Tukey's test, there's Fisher's test, there's Bonferroni, there's the modified Bonferroni. But we don't need to get into all that. There's different reasons to use different Posthoc tests. Tukey's is a very common test. It is used in lots of different ways. It's a fairly conservative test. That is, other Posthoc tests allow you to make decisions where you might be more likely to make a type 1 error. Tukey's test is pretty good Posthoc test. So honestly significant difference. Okay. Well, let's get this value first. Before we go to Q, let's do this. Mean squares within. So here's the within groups. There's the mean squares. So this is 1.30 divided by 5. That's the number of people in each of our groups. Now Q is called the studentized range statistic. It's called, I didn't make up this name, the studentized range statistic. And in fact, this is one that you look up in table B5, okay? So I'm going to get the book. I'm going to go to table B5. And what we're going to do here is we're going to look at the instructions. In a way, these tables each have sort of like instructions. It says along the left-hand side, it says degrees of freedom for the error term. Now, this is something that we need to pay attention to. We're only going to, this is the basic analysis of variance. There are other flavors of analysis of variance. And for our consideration, this here is known as the error term because it tells us this is the variability that we don't know where it comes from. This variability hopefully will be partly due to the treatment. This is the residual. Again, I don't want to get too far down that rabbit hole, but this is what they're talking about for error term. So what are our degrees of freedom? Is 16. So we look down that column to 16. And then along the top, and we'll do this on Zoom. I'll show you guys this as well. Along the top, it says number of treatments. So how many treatments do we have here? We have 4 treatments. So I'm going to look down that column until I get to 16 for degrees of freedom for the error term. So this is 4.05. And take a look at your table B5 in the appendix and see if you can't find that. And now we're just going to solve to get our Tukey's HSD. 1.3 divided by 5 equals 0.26. But remember to take the square root. People oftentimes forget. So that's 0.51. So HSD is equal to 4.05 times 0.51. Okay? And so 4.05 times 0.51 equals 2.06. Okay? 2.06. Our HSD in this case is 2.06. Now, what do you think we do with this value? Now, if you said that you think that we compare this to some critical value, that's a really good guess. It happens to be incorrect in this case, right? I mean, we looked at critical values for Z, for T, for F, but for HSD, and it's in the name, this is the honestly significant difference. This is how far apart any 2 means have to be for them to be statistically different. Let me say that again. This is how far apart, it's like a ruler, this is how far apart 2 means have to be for them to be significantly different from one another. Okay? I mean, if it's more, so be it. Okay, so now what we're going to do is we're going to do this. We're going to do all of our pairwise comparisons. We started off this way 2 videos ago, right? So, are these 2 means more than 2.06 apart? The answer is yes. So we're going to put an asterisk there. This is different than this. Are these 2 more than 2.06 apart? Yes, they are. Okay. What about these 2 means? No, we're going to say not significant. Okay. How about this and this? Nope, not significant, right? How about this one and this one, the means, and we're going to say, yep, that's different. And then this one and this one. Nope, that's not different. Okay? Now, you can go through and say, make each of the 6 pairwise comparisons. God, if we had 5 groups, it would be even more. 6 groups would be even more. Or we could try to make some sense out of this pattern. The data are telling us something. Okay? Everybody good here? When I calculate this, this is my ruler to go back and say, are these different? Are these different? Are these different? So we rejected the null. What it looks like to me for this data set is that the Taylor-Swift group is different from the other three, and the other three are not different from each other. Okay? This is a way to summarize what we see here. Wow. Okay? A little bit complex. But when we have four groups, we need to up our complexity of our analysis in order to do this correctly. Okay? And so here's our statistical conclusion. And the way I would write this, by the way, in a journal article, let me go and do that, and it's going to be a little bit more complex, right? Analysis of variance revealed a statistically significant treatment effect, and I will put my F 3 and 16 equals 7.42. This is my observed F. I think it was 7.42, right? P less than 0.05. But of course, anybody reading this in a journal will know, right off the bat, will know that just because you have a significant treatment doesn't tell you where that is, where that treatment is. In fact, I'll tell you a little bit of a story. I remember when I was a research assistant, after I got my bachelor's degree, I worked as a research assistant at Colgate University, and I was working with a really good professor there. His name is Scott Crayley. And we were doing research with more than two groups, so we're using analysis of variance. And we would do it, and then he would say, well, now we have to do a Tukey's test. And I said, well, why do we do the analysis of variance? Why don't we just go to the Tukey's test? And he explained to me the reason, and I'll get to that in a minute. But I took this course that you're taking right now, I took twice and got an A twice, and still didn't really realize why we were doing Tukey's. So I'll show you in a minute. Anyway, initial statement, and then we're going to say follow-up Tukey's test revealed that the music group was significantly or let's do this. And it's okay to revise. Of course I'm going to revise. I'm a good writer. The music group remembered significantly fewer words than the quiet group, the white noise group, and the music group without lyrics. And none of those groups were different from each other. Okay? So it's much more complicated, but your conclusion matches the steps that you've done here. First analysis of variance, and then follow up with Tukey's. Now, as a researcher, I want to make sense of this. We have four groups for a reason, not just to have fun. And what we can say is, well, was this decrement here, was that due to the music? I would say it's not specifically due to the music, because here's the same music over here, and we didn't see any kind of decrement, right? So just the music alone didn't do anything. Well, did the decrement here, was it due to the fact that this group was just in a noisy situation, compared to the quiet? The answer is no, that's not the cause, because here's a group that's in white noise. We've made sure that it's the same decibel level, so it's the same amount of noise, and we didn't see the decrement. So what is our conclusion here? Well, it looks like the decrement that we see here was probably caused by the lyrics. Because here's the music without lyrics, we didn't see any problem. Here's the noisy group, didn't see any problem. We saw it only when we included lyrics. And of course, I've made these data up, right, to serve my purposes. But I can say, well, because if you're trying to remember a list of words and you're listening to other, music with words, then that's probably going to compete with what you're trying to remember, okay? Now, if I wanted to, I could have made the example so that we saw a decrement here and here and here, right? And if we did this experiment, we might find that pattern. If I saw a decrement here and here and here, my conclusion would be different. I would say that any noise is going to bother you when you're trying to remember this word list, right? If I saw a decrement here and here, but not here, then that gives me some evidence that it's the music that's disrupting. Okay, so the pattern of results here, and this is why I use this example as a teacher, the pattern of the results will inform you about why we're seeing a decrement here. Now let's rewind everything. Let's go back to when we started this research, and if I just had this group and this group, if I just had this group and this group, and we did a t-test and we found that it was significantly different, I wouldn't know if it was music, if it was noise, or if it was the lyrics. If we just had these two groups, I would be unable to differentiate what component of listening to that pop music, what component caused the decrement. When I do it this way, I'm able to assess or infer that it looks like the lyrics. If it was music, we'd see a decrement here. If it was just noise, we'd see a decrement all the way. All right? This is what good research is all about, trying to tease out the variables, because if we just did this, we might be fooled and say, don't listen to music when you're trying to study. Well, I would, based on these data, I would say, okay, since I included this, I know it's not the music, right? Because this was the same music, just minus the lyrics. So this is how research can get more and more complex. And in fact, the reason that we talked about error determinism within groups is because there are other analyses of variance that aren't this simple. And I chuckle because it's not really simple, right? It is not simple. But this is the most basic form of analysis of variance. I will tell you another flavor of analysis of variance of a research project, and that is something that we've already talked about, so I'm assuming that you are able to understand this. That is, the experiment that I described as part of this whole analysis here was that there were 5 people in this group, there were a separate 5 people in this group, separate 5 in this group, separate 5 in this group. That is, these 5 people are different than these 5 people, these 5 people are different than these are different than these, right? And that's called what? A between subjects design, or an independent measures design. You can imagine, I hope, think about this, where we use the 5 subjects here. We ask them to, learn that list of words in the quiet condition. Then we put the same 5 subjects in the music condition. Then we put the same 5 in the white noise. Then we put the same 5 in the Taylor Swift without lyrics. That is a within subjects design. A within subjects design where we use the same people, or pre-post in a way, or repeated measures. Remember, those things are all the same pretty much. If we do that kind of an experiment, then we need to modify our analysis of variance. I'm not going to do that, folks. I'm not going to do that. But you may do that when you are practicing your profession, okay? You may do that if you go on and get a PhD and are working with a professor at some university and they do this kind of design. If you do, then you will use a modified version of the analysis of variance, okay? It's beyond this course, I think. I mean, we could do it, but we're running out of time as well, right? But I just, we've learned a lot of stuff. We have a lot of tools in our statistical toolbox, and we're going to leave some of the tools shrink wrapped, right? Like Hartley's F-max. Remember, Hartley's F-max is a test that we would use to see if our assumption of homogeneity of variance is a good assumption, right? Hartley's F-max. But we didn't do that. But I would want you to, here's a hint, I want you to know that that's what that tool is for if you ever need it. Likewise, we have an analysis of variance where we have 5 different people in each of the groups. That's the one that we did, okay? But there's also an analysis of variance where you're using the same 5 people repeatedly. What's nice about that is you sort of already know these 5 people because you tested them before. You already know these 5 people, right? You're testing them all the way through. And by you already know, what I'm saying is you can get rid of some of this variability. It becomes, let me back up. I don't want to say get rid of it. You never get rid of it. You don't get rid of it, but you account for it. So it can come out of this thing that we call the error term. Okay? But that's enough, right? That's enough. And by the way, the next set of videos is going to be completely different from this. We've sort of reached our pinnacle here with trying to assess differences between groups, okay? This is as hard as it's going to get for us. When you go on to graduate school, you can deal with the more complex studies. But the next series of videos, we're going to be asking a completely different question. Instead of differences, we're going to look at relationships between variables. But I'm getting ahead of myself. So email me if you have questions. And yeah, we'll be ready to move on for the next video.